So welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Sarah Dean, who is an assistant professor in the computer science department at Cornell. Something about Sarah, so she obtained her Bachelor of Science from the University of Pennsylvania, and she then moved to the other side of the country to get a PhD in electrical engineering and computer science from UC Berkeley. Her research is about the interplay between optimization, machine learning, and dynamics. And the research of her group in general is about understanding the fundamentals of data-driven control and decision-making. Applications for this kind of work range from robotics to recommendation systems. As you've seen in the bio I shared, she has won a number of awards. And today we are very excited to hear more about this particular subject, which is learning dynamics from bilinear observations. And so without further ado, Sarah, go ahead. The stage is yours.
All right, awesome. Thank you so much for the introduction. Hello, everyone. I'm happy to be here talking about this work. If you want to interrupt throughout with questions, I'm happy to make this interactive. I will, be happy to answer questions both at the end and throughout. So let me talk a little bit about learning dynamics from bilinear observations. I realize that my slide is not quite right. It's no longer June, but we're close. This work is motivated by the existence of large-scale automated systems, which are powered by machine learning. And now some of these systems, I think, are maybe familiar to controls and autonomy community, like maybe power plants or robotic systems, where we have like engineered, built physical systems that are automated, that are performing some crucial tasks. But in our modern world, there's another type of automated system out there, and this type is maybe particularly powered by machine learning and very data-driven. And these are, let's say, social digital systems. So things like social media, e-commerce, online news, right? The multitude of ways that we're connected online. A lot of that is mediated also by some sort of automated system. And that is kind of my motivation for the talk today. So let me start by defining some terms, thinking about machine learning and thinking about feedback. So the heart of machine learning is this pipeline from a bunch of training data, a bunch of examples, towards some data-driven model. And model is something that takes observations as input and outputs predictions, right? And we can do this in all sorts of domains, and indeed we have, and this has led to the great success of a lot of new machine learning. For example, like let's think about a social media system. Our observations about an individual might be their historical interactions on our platform. And we may have a model that takes in those historical interactions as well as some other context information about the user, and then predicts the probability of a new interaction, right? So these are sort of click prediction style models that power a lot of online advertising, online recommendation systems. And so this is great. This is what prediction means. This is like the basic idea of machine learning, but that's not usually where the story ends once we start to use these models, right? In general, we have the data and the observations coming from some environment, coming from the world in some way. And we don't just make a prediction for the fun of it. We actually make a prediction in order to take some action, make a decision, right, according to some policy. So that action, for example, let's say recommending which news article to put at the top of somebody's news feed, actually affects the world or the environment that our data originally came from. And so we end up in this feedback loop where feedback arises because actions like recommending some piece of content actually impacts the world. It impacts what users know, let's say. And this also causes some potential complications in how we train models because the training data itself will be correlated due to these dynamics and feedback. And these are sort of two things that I want to talk about today in the context of these social digital systems. So in particular, I'm actually going to spend the first half of this talk focusing on kind of like a motivation. Right, we don't often think of these recommender systems in the same language as control systems. And so I want to spend some time building up some examples of what could happen there and what the implications are. And then the second half of the talk, I'll actually get into the meat of things, like learning dynamics from bilinear observations. And I'll kind of try to motivate in the first half and connect to the second half why this bilinear observation model is so crucial, and why we might want to learn from data here. All right. So starting off with this personalization motivation, I'm going to start by just setting up the problem, setting up some notation for what might go on here. Then I'll talk about a certain type of dynamics, assimilation dynamics. And then I will get into some implications and design principles around some notion of harm. Okay, so the setting that I want to study here is preference dynamics, where the interests of an individual may be impacted by recommended content. That's kind of our core idea. So the feedback loop is between a recommender policy, which recommends content, could be a news article, could be a playlist, to a user. The user in response expresses preferences, through engagement or through explicit actions. And those preferences are used by the recommender policy moving forward. So let's put on our controls hat and add some math notation. So the recommended content in this case is sort of like an input, right? It's the policy chooses an input for recommended content, which I'll call UT. The user, the person we're interacting with, may have some preference state, so like some notion of what they like to see, what their tastes are. And I'm going to think of this as a state and call this X sub t. Generally, this is a hidden state. And what we can see instead is just the expressed preferences, right? So engagement signals, other behavioral signals, which I'll call YT. Okay. So the one piece of this talk that we'll have throughout is a certain type of observation model, in particular, a bilinear observation model. For this first part of the talk, I'll make this the simplest bilinear model possible, which is just an inner product between the state and the input. So this says that the observation, the user behaviors, in this case, we're going to say that they're scalar, is the inner product of the state and the input plus some disturbance or some noise. And why is this a reasonable model? So inherently, a user responds to a piece of content, and that means that there's sort of a interaction between like their preference and the content itself. So we have to have more than just a linear relationship, and bilinear is maybe the simplest one we could go. And it turns out that in practice for years now, we actually see that these kind of relatively simple bilinear models are effective at capturing a lot of large-scale preferences. So for example, matrix factorization is a very kind of classical, but still relatively popular method for modeling user preferences, where, let's say the expressed preference of user I for content J is, you could store this all in one large matrix, number of users by number of pieces of content. Many of these matrices exhibit approximately low rank structure, meaning that we can factor them into a factor corresponding to user preferences. So this would be like the preference of user I, and a factor corresponding to the attributes of, let's say, movies. So this would be movie J. And these types of models gained prominence in the recommendation world back in, I think, 2009 during the Netflix Prize, where the task was movie recommendation. But they're still quite important today. And even though models in production today are not necessarily pure matrix factorization, they often have some kind of two-tower architecture where predictions are made by these types of inner products for some learned latent representations. So that's a little bit of motivation for this bilinearity. And we're going to stick with this type of bilinearity throughout the talk. Okay, so that's our model. We have the content, the preference state, and observation is bilinear. And of course, in a dynamical setting where our actions have consequences, the content actually causes the state to change from some initial state at time t to a new state at time t plus 1. All right. So that's the basic setup. Let's go through a couple examples of preference dynamics. And here I'm mostly going to be talking about assimilation style dynamics. So I'm going to illustrate this here with preferences and recommendations that kind of lie on the unit sphere. So really what matters is their direction, not so much their magnitude. And that's just kind of convenient for illustrating some things. The idea of assimilation is very simple. This idea comes from literature on opinion dynamics, actually kind of connected to network science. And the basic idea is that interests become more similar to the content that is recommended. So the preference state at time t+1 is sort of proportional up to the unit norm scaling to the previous state plus the content times some positive factor, some positive, let's say, step size that determines the magnitude of the update. So we can illustrate this visually. Let's suppose that this gray line is the user's current preference, right? So in this case, we're in 2 dimensions. And this is a music application, and I recommend this red song here. This red arrow represents the attributes of some song. And in this image, because this inner product is going to be positive, right? The angle is acute. I have, a happy, instance. I get positive feedback. My output signal is positive. The user likes this song. And as a result, also of the recommendation, the new preference sort of moves towards that song, right? I'm more interested in this type of music than I was before. That's the basic idea of an assimilation dynamic. Now, of course, this is very simple, but I think it's already illustrative. There's one other model that adds one slight level of complication, which is biased assimilation. This is actually no longer an almost linear model. We have one additional kind of nonlinearity, which is that rather than always becoming more interested in content that's recommended, whether you become more or less interested is actually directly related to how much you enjoyed it. So in our first example, the user gave positive feedback and their preference moved towards the recommendation. But even if the user had given negative feedback, their preference still would have moved towards the recommendation, which maybe isn't so realistic. So the bias assimilation model allows us to account for this switch so that the update, rather than just sort of some fixed constant eta sub t, is proportional to the affinity itself, right? Where affinity is the term that I'll use to describe, right, the user's response, right? The measured output, whether it's clicks or listen time, is roughly determined by the affinity, this inner product. But also, so is their preference update. That's the model for bias assimilation. And there's a couple other ways to model bias assimilation that also come from the opinion dynamics literature. But this particular model was proposed by some folks in 2019. And let me illustrate what happens. So, right, we had our previous example of a song. Let's say that I now recommend instead some other song that's totally the opposite of the song that the user enjoyed, right? So I don't know, something from pop to heavy metal. Now the user is really not into that recommendation. They really don't want to listen at all. And we would see that by a negative response that's measured in their behavior. Also, their preference would be pushed away from this type of music, actually towards the exact opposite type of music, right? So we now see this like effect of either going towards or away from attributes of content. And like I mentioned before, this was proposed in 2019 as a model of opinion dynamics. So these models have traditionally been used actually to study the kind of global opinion dynamics and phenomena like polarization, let's say. And this prior work, it really matters whether you use an assimilation or bias assimilation style model because you end up with kind of inherently different stable outcomes, let's say. And so let me just summarize that a little bit. Here, the focus is on recommendations that are made globally. So everybody sees the exact same news stories, the exact same music. There's no aspect of personalization. And in this case, under assimilation dynamics, we would see a homogenization of preferences, because the dynamic is always encouraging people to, agree with what they see or be more interested in what they've seen. And if everybody sees the same stuff, then everybody becomes more similar. And so we can, make a cartoon of this by saying the gray arrows here are representing initial preferences, whereas the black arrows represent the resulting preference, right? And so we see this collapse of some, initial preference is quite different, resulting preference would be would be pretty much the same. So this is what I'll call homogenized preferences. On the other hand, in biased assimilation, due to this nonlinearity, we would see still some type of collapse. So preferences, right, which might start in all directions, still sort of collapse, but now they collapse to one of two poles. So one direction or the other. And this is sort of referred to as polarization. And this has been studied in previous works in sort of like both in network structures and also these global recommendations. And they show that, even when these global recommendations are quite random or vary in some way, and so there's no real convergence to a fixed single opinion, you still get convergence to one of two poles. So that's kind of interesting. It shows the difference in these opinion type models. And, maybe it gives us a way to think about public opinion and what's going on these days politically. But how does it affect the automated systems that we build? When we build personalized recommendations, are we exacerbating these issues, or how should we think about this? And so actually in the personalized setting, the story is a little bit different. It turns out that these assimilation dynamics are not so distinct. So regardless of whether the assimilation is biased, so regardless of whether we're on the left or the right in terms of our preference update, if we make personalized recommendations, then sort of the same thing happens, or almost the same thing happens. Let me illustrate with a very simple example. Let's suppose that I always recommend the exact same content. So let's say I recommend the same musical artist every day on your Spotify homepage. Then under either of these dynamics, the user preference state will be as follows. It will be some combination of the initial preference state of the user plus the fixed recommendation that I keep making. And the coefficients on these two terms, well, on the initial preference will be positive and decreasing. So less and less weight on that initial preference. And this portion that has to do with the recommendation is increasing in magnitude. And the one way that bias assimilation matters is that the sign of the second term will depend on the sign of the initial inner product between the preference and the recommendation. So essentially, if the user likes the artist to begin with, if our recommendation algorithm is even just passing a slight bar of the user doesn't hate it, then this will be positive, and it will be exactly like what happens in just standard assimilation. We see that a user becomes more and more interested in this recommended content over time. So, Spotify shows me some artists. I kind of like the artist. I now become a super fan of the artist, and I'm kind of following everything they do. That's what this model says. And so assimilation kind of has this one characteristic, actually, and it's not so different whether it's biased. And so what are the implications of this model? I won't go into most of the details here because I mostly just wanted to start to get us thinking about dynamics models in these settings. But we have a couple in a paper that was at the Economics and Computation conference a couple of years ago. So the first implication is actually for the practice of designing recommender algorithms. And it says that it's actually not necessary to identify preferences in order to make high affinity recommendations. So in order to make good recommendations. Why? Because we see that in these models, users sort of adapt to recommendations as long as they start out good enough. And so we might think that we're, learning somebody's preference and being really smart when actually we're just seeing the response of this assimilation dynamic. Another implication, kind of calling back to this polarization or homogenization results from before, is that we won't necessarily see that because now individuals are exposed to different information. but we still might see a preference collapse towards whatever the most commonly recommended content is. So for example, if our initial preferences are quite diverse, but the body of content that we have does not exactly match everybody's niche, we would see this collapse in preference. So we call this sort of a loss of diversity. And then finally, if we wanted to counteract that effect, it's possible. So these dynamics, you can design algorithms that account for them and that do something like non-manipulation, for example. So they don't change the initial preference at all by randomizing recommendations that are made in a particular way. And we sort of propose an algorithm for how to do that. So that's sort of the basic idea of these preference dynamics. And now I want to talk about another set of implications that has to do with another concern when designing recommender algorithms. And that is harmful recommendations. And here the idea is that preference dynamics lead to a new perspective on how recommender systems can cause harm, right? So let's think of maybe the simplest possible definition of harm. There's certainly others, but just as a starting point, let's say that harm is just caused by the consumption of harmful content, right? So to be more lighthearted, I think we'll stick with the music example. And suppose that, there's some song that will just really get stuck in this person's head and they'll be haunted and they would really like to never listen to this song, right? And so harm here is just caused by a recommender system which surfaces this content to somebody. And we can even make our lives simpler and suppose that we know which content is harmful. So here, I'm going to stick with this music example. I'm going to say that in blue and red are a bunch of different songs. These arrows represent their embeddings in some, latent space, their characteristics. And I sort of know that one of these songs, this red song here, is harmful in the sense that, a user will regret listening to it. And the user's preference is illustrated here in black. And so there's a very simple way to solve this problem. And it is that if my recommender system knows everything, I just never recommend, right? I can rule out recommending this red song. So that might solve the problem, except that we're going to allow users a little bit more choice than just passively consuming recommendations. Given recommendations from let's say, your Spotify homepage, the user might select a recommendation with some probability determined by how much they like it. So if you surface a really good For You playlist today, the user is pretty likely to click on that and not go any further. However, with some probability, the user may also, go off and click around, search for different artists and find something themselves. They might choose content organically as well. And so under this model, actually, we need to think a little bit more carefully about what causes or prevents harm. So to illustrate with this example, in the absence of a recommendation, the probability of clicking on any one of these songs or listening, let's say, to one of these songs is proportional to the inner product between the user's preference and the song, right? And so we kind of see this ranking of probabilities where there's, some probability that the user will stumble upon and click on this harmful song. But if you make a recommendation, that changes. So let's recommend one of the best possible songs, one of the highest affinity songs right here. That changes the probabilities because now the user is likely to accept the recommendation. And so we have less chance that the user will stumble upon this, song that gets stuck in their head forever. And so if there's no preference dynamics, if there's no downstream impact of this recommendation, then actually the harm minimizing policy, as you might guess, is actually the engagement maximizing policy, as long as you exclude harmful items from the recommendations, right? It means that actually the practice of trying to get users to click or engage or listen is actually somehow good for them as long as the recommender system knows what's harmful, because we can't trust people to go out themselves and find music to listen to or something like that. So that's a nice story, but I think there's a couple things wrong with it. And immediately one of them is that it doesn't feel right. There are downstream impacts of recommendation. And so with preference dynamics, without preference dynamics, actually, it wouldn't matter whether I recommend this song or this song. in terms of minimizing the probability of harm. Because both of these are sort of equally attractive to the user. They're equally likely to accept these recommendations instead of going off to look for music themselves. However, if we think of a very simple, even assimilation style dynamic where a user becomes more interested in music that they've listened to recently. So I get in the mood for a certain style of music. Then the downstream impact of making this left or this right recommendation is very different. We have the probability of future clicks, if I make this left recommendation, has really decreased harm, because this harmful song, let's say it's like Bolero's, what is it called? I can't remember now. Something that really gets stuck in my head. It's very different from this recommendation. And so I'm not really in the mood to look for it anymore. So this sort of like successfully leads me away from looking to do something that I'll regret. Whereas this other song, while not harmful in its own right, is quite similar to a song that I will regret listening to. But it might put me in the mood for that song and sort of increase my chance of listening to the song in the future. And so with preference dynamics, we now see that there is this additional level of responsibility or harm that can be caused by recommender systems. So the main implication here is the motivation of a new recommender objective that has to take into account these future impacts and future probability of harm, which inherently will rely on dynamics models. And so this is a paper that will appear at KDD later on in the summer that we kind of handle this. But now I actually want to depart from some of this like very specific modeling for recommender systems and think about this from the perspective of learning and system identification, right? So I've posited a couple of assimilation models. I've motivated why they're important and how their implications matter. But certainly any of the models that I put on the screen, any of the math equations are probably not going to be that accurate at describing any one individual's behavior, right? There we want something more flexible and more data-driven. And so that kind of brings me to the end of this motivation where I wanted to introduce a couple of dynamics models to get us thinking. And forward to the second part of the talk where I'll focus on actually learning these models from observations. All right. So here I'm going to start by just defining the setting. Very inspired by our previous setting, but now a little bit more stylized so that we can set up a rigorous kind of learning and estimation problem. Then I'll describe the algorithm that we'll use to learn these dynamics and go through some results. Okay. So the problem setting here is that we don't know ahead of time the dynamics, so how a user's preference will change, let's say, or the measurement function. What I mean by that is exactly the user response. Instead, what we have is a bunch of observed data. So an observed trajectory of inputs, UT, and outputs, YT. And here we're going to kind of stick with the previous model where inputs might be high dimensional. They might represent characteristics of content, some embedding. For simplicity, we'll just stick to scalar outputs, although a lot of this generalizes as well to the multi-output case. But let's think of scalar outputs. So, this is like how long a user listened to their Spotify daily playlist on that day. And yes. And the input corresponds to, right, the attributes of the playlist, right? So, one day I recommend a playlist with more rock, one day more pop, one day more jazz. And I can observe, how long does the user listen to each of these playlists each day. And the goal is to identify the dynamics and measurement models from data. So identify how the preferences are actually updating under the hood and how the preferences are impacting the measurements that we make. And we'll do so not in full generality, but in a linear bilinear setting. So that we assume the dynamics model, the dynamics update, is linear, and the measurement model is bilinear. So starting with the dynamics model, we have kind of our familiar A and B matrices, which determine, right, the evolution of the autonomous dynamics plus the effect of the recommendation. And then the measurement model is bilinear, just like we motivated before, but I've added one extra parameter of flexibility. which is this C matrix, these linear parameters that transform the state before doing the inner product. This allows us a little bit more flexible representation. It means that we don't have to, say, represent the user preference and the attributes of a playlist in exactly the same dimensional space. We could represent them slightly differently and learn some mapping between them with this matrix C. So we have A, B, and C are sort of our dynamics, and our measurement matrix, like we often see in linear systems, but knowing that actually our measurement is not just linear, it's bilinear. All right. So that's our setting. I'm now going to tell you how to solve this problem. This is how I would identify those unknown dynamics. The input to our algorithm is a bunch of data, right? It's the trajectory that we observe. This is sort of temporally correlated data that's actually coming out of a dynamical system based on recommendations that we make. We will have a history length L. This is a parameter for our regression problem that I'll tell you about more later. And we assume knowledge of a state dimension N. So relaxing that assumption, we only need it for certain parts of this algorithm, and relaxing that assumption is still for future work. Actually, I should say while I'm here, this portion of the talk is still relatively new work. We're still kind of writing up the paper and hopefully getting it on archive in the next month or so. But this is fresh. There's a lot of open questions and ideas here. So I'll highlight a lot of those as I'm going through. Right. So, okay, how does our algorithm work? It's going to have two steps. The first step is regression. We're going to regress the outputs that we observe at each time t. So if we think about a particular time t, we regress that output against this term, which let me unpack. First, the term has an inner product with also the input at time t, right? So this is, how long I listen to a playlist on a particular day. I'm regressing this partially against what playlist was recommended on that day. This is intuitive. We sort of have to do this because users are always responding to recommendations, right? Not just in a vacuum. And so that's where this term comes from. But the second term here is now the sum of the effects of previous days. And this models the fact that if preferences shift in response to recommendations, then we have to account for a bunch of previous recommendations that we made as well. And this is where our history length L comes in. So let me illustrate that here. We consider all the playlists from the past L days as well. And then this parameter G is the parameters that we're regressing. We're trying to learn some parameters G, where G is the dimension of the input, U, so that's P. And then also we have L of them because we're looking L steps backwards in time. So it's a P by P times L matrix. Right. So this is our main sort of learning or regression step. This is where we try to figure out how to predict responses from users based on past recommendations that we've made. And then our second step, thinking, in the full restrictive setting of identification, is actually to try to go and find these parameters A, B, and C. And so here we can leverage a lot of existing work in the system identification world, like finding A hat, B hat, and C hat through a Ho-Kalman algorithm on G hat. And maybe I'll explain why this makes sense in a moment. Let me point out that the Ho-Kalman algorithm is where we need to use the knowledge of the state dimension. And so if we're just happy with sort of a predictive model or the output of this regression, we can actually leave behind the state dimension question. It's only when we want to do parameter estimation that we have to worry about state dimension. And so there's some flexibility depending on what you want to do with the resulting model. Okay, so that's our algorithm. This is what we should do given the data that we have. Now let me talk through estimation errors, moving towards our results. So how well does, the main question to ask is how well does this algorithm work? If I give you a bunch of data, sure, you can make a prediction, but what about, quantifying your uncertainty or telling me if that was enough data? Those are the results that we're looking for. So let me define estimation errors. First, right, we're calling this step one, this regression step, where we regress the output at time t against the inputs from time t to t minus L. This is actually a biased, it is an estimate of the Markov parameters of the system. And I mean actually Markov parameters in the traditional linear system sense. So the matrix of C times B, CAB, CA squared B, all the way back L steps in time, right? This occurs because if I think of the effect of the input k time steps in the past, that will have, affected the state by a power of a to the k. It will have, entered the state through this matrix B, and then it will affect the output through this matrix C. And so for this reason, G is actually estimating the Markov parameters. However, it is a biased estimate because I'm doing this truncation. I'm only truncating L steps back in the past instead of looking all the way in the past. And so let me try to reformulate our regression problem to think of it as just sort of a more generic high-level linear regression. What's going on in this second term here? What I'm really doing is regressing y against the products of ut and then ut minus 1 through ut minus L. I can write this as a Kronecker product, and I can call this long series, this L length window, u bar, right? And so I can rewrite this regression as essentially a non-linear, really a bilinear, I guess quadratic sort of, featureization of the inputs times, some unknown parameters. And once I have this nonlinear parameterization, this is really a linear regression problem. And so thinking of the problem in this way, I can now leverage some tools from like linear regression analysis. And to do so, I'm going to first define the data matrix. So the data matrix is the matrix that contains all of our covariates for the regression problem. So U bar, Kronecker, U for all the time steps that we have. So L minus 1 through T. And let me just spend a little bit of time talking about this matrix. I think I have time. Yeah, I'll talk a little bit about this matrix because it's going to appear.
Yes, you have plenty of time, Sarah.
Okay, great. So what is this matrix doing? This matrix is going to play an important role in telling us how confident we can be about the estimates that we make. And so let's say I'm given inputs over time. I'm illustrating that with this vector. Then the first component of this data matrix, these U bars, have a very specific kind of toplet structure to them. So, right, this first several inputs would define the first row of this matrix. And then the next row would be shifted down by one in time, right? So we sort of already see this kind of banded structure in this matrix here, right? And so on and so forth for the next rows. So this first component is a sort of a toplet or a circulant structure. And these types of matrices often appear in system identification problems because of the need to consider this moving window of the past, right? But we have one more complication on top of that. That's not the only piece that we have, because we also have this multiplication by this other input. So we also care about the effect of the current playlist, right? Our ability to measure somebody's preference is sort of multiplicative in the current recommendation as well. And so I also have the inputs affected here sort of by some row-wise product, which I'm not really defining formally. But the intuition is that there's this toplet structured matrix and some row-wise product by, right, this matrix, which is, exactly also contained in the toplets matrix. So these are very dependent matrices. The toplets matrix itself has this like dependent structure between the different rows and columns. And now we have this row-wise multiplication by yet another dependent set of variables. And that's kind of going to give us this data matrix U tilde. Okay, that was like maybe a lot of description of a matrix, but now let me get to our results, and we'll see why this matrix matters. So there's two main results that I want to go through that I'll summarize a little bit, and then I'll spend some time talking about open problems as well. So before we state results, I do now have to make some assumptions, which maybe you've guessed based on some of the pieces of the algorithm. One assumption we'll make is that the process and measurement noise, so W and V, so that the process noise affects the evolution of the state of the preference, and V affects our measurement of the user response. We assume these are IID zero mean and have bounded second moments, so bounded covariances. We don't actually assume that the inputs are anything in particular, except right now we will assume they're bounded. So there's some bounded inputs, like the attributes of the playlist we recommend are bounded in some sense, which is quite reasonable. And then third, the dynamics A, B, and C, the dynamics matrices are observable, controllable, and strictly stable. So when I say observable, I mean that A and B are observable in the classic, A and C are observable in the classic linear system sense of the word observable. I mean that A and B as a pair are controllable in the classic linear system sense of controllable. And strictly stable means that the matrix A has a spectral radius of norm less than 1. So its maximum magnitude eigenvalue is norm less than 1. And so under these assumptions, we have our first result. I'm presenting an informal version of the theorem here, and this is a result on the estimation of G, the Markov parameters. So we can say that with high probability, where delta is a failure probability, so this you can think of as being like a 95% confidence interval if we set delta to 0.05, then the error in G, G hat minus G, the real Markov parameters minus our estimate, measured in a norm shaped by our data matrix, which I'll point out what that means in a moment, scales as follows. It scales up to constants and I think logarithmic factors, like square root p squared L over delta. So this is the dimension. This is sort of like the effective dimension of what we're trying to estimate, divided by this failure probability. And then I'm hiding some constants which are important, but I won't go into for the talk, that have to do with how big the noise is and also how stable our system is. And that's sort of, this is roughly a classic estimation style term with some specific constants that come from the system at hand. And then our second term is the spectral radius of A to the Lth power. So remember that the spectral radius is less than 1. So that's good, because then this number can be quite small, times square root t, the amount of data we have, times a constant that just depends also on stability. And so the second term comes from the biased part of our bias estimation, right? We truncate our regression to only consider L steps in the past, meaning that there's some additional effective history past L that we're leaving out. Here, because we assume that A is stable, as long as L is sort of like logarithmically sized in T, this term is effectively negligible, and we can focus mainly on our usual statistical estimation style result. But this decomposition illustrates why stability is important. Otherwise, we have this term that is actually growing in the amount of data that we have, which is not what we want. What we would like to say is that as our data gets larger, the error gets smaller, right? But this term is negligible as long as L is sufficiently large. So where is the term that tells us that as we get more and more data, our errors get smaller? That term is not actually explicit in this bound. It's implicit in this norm, right? So the way that we're measuring the error in our Markov parameters is an ellipsoidal norm, where the ellipsoid is defined by our data matrix, U tilde transpose U tilde. That's essentially our data covariance matrix, if we want to think of it that way. And what this means is that if this data covariance matrix gets quite large, this error bound implies an absolute error bound of something very small, right? And so the shape of this covariance matrix matters a lot. I'll return to this a little bit later to say, how do we get towards showing errors decrease over time? But first, let me also mention our second informal theorem on system identification. So our first is about Markov parameters. Now we want to actually say how well did we do at estimating the parameters a hat, b hat, c hat. So we're going to suppose L is sufficiently large. Then up to similarity transforms, we can estimate A, B, and C. So what I've written here are similarity is a comparison between A and a similarity transformed A hat. This is because in linear systems with partial observation, we don't have a unique realization, right? Many different underlying state spaces that can be rescaled to give you exactly the same input-output structure. And so, we don't have any hope of getting an exact A. There's not really even a well-defined notion of an exact A. But up to a similarity transform, we can identify these parameters also in the ellipsoidal norm shaped by U tilde and show that this is bounded by the error in the Markov parameters, essentially. So this is a result that has to do with the stability of the Ho-Kalman algorithm. And there is also some constant here that has to do with controllability, observability, and also the dimension of the parameters we estimate. So this theorem is just to say that we can do parameter estimation if we can do Markov estimation. Okay, but now I actually want to kind of summarize. The informal summary of both of these results is really just that with high probability, we're paying an estimation error, which is sort of polynomial in the dimension of what we need to estimate. That's good. That's what we're normally looking for. And then if I account for this like shaped norm, the ellipsoidal norm, it is divided by the minimum singular value of our data covariance matrix. And so this is what I was alluding to before. If we can show that this minimum singular value, just geometrically, the minimum singular value is sort of the radius of our smallest, right? An ellipsoid has radius in, n dimensions, like however many dimensional, I think p dimensions in this case. No, sorry, the dimension of our unknown parameter, right? We have an ellipsoid, and so there's radiuses in all these different directions. The minimum radius is the minimum singular value here, right? So this is where we have sort of the least data in our covariance matrix. So we divide by that radius, and that tells us how certain we are in an absolute sense, right? So we have some polynomial dependence on the dimension divided by this minimum singular value of our data matrix. And now if you're familiar with a lot of system identification work, this is where we think about something like persistence of excitation. How do we ensure that this minimum singular value is sufficiently large? Like how do we make these errors go down as we get more data? And it really has to do with the inputs that we select. So really what this question, what we're getting at here is a sample complexity question. How large does T need to be? How large does the trajectory need to be to guarantee a bounded estimation error? So like I said, this is actually a work in progress. And so we don't have a formal result here, but we do have a conjecture. We are pretty sure that if the inputs are chosen IID and sub-Gaussian, and that T is large enough in a reasonable way, then with high probability, this minimum singular value will scale linearly in T. So every data point is increasing the size linearly. And if this conjecture is true, then we would have the following corollary, that our estimation errors decrease at a square root dimension over T rate, which is the type of rate that we like to see for finite sample complexities. We believe this conjecture is true, based partially on just a lot of like numerical experiments, where we can plot actually the minimum singular value of this matrix for different amounts of data T, where we just choose the inputs IID. I think this plot's from Gaussian. And indeed, we do see something that looks like a linear increase. I'm plotting here the median and quantiles over like 100 trials. It looks quite linear. However, proving this actually is something that we're still trying to figure out, or we're looking actually to alternative methods for designing inputs that guarantee this linear increase. Because the random design, analyzing it would involve analyzing the structured random matrix U tilde, which I know I belabored a little bit earlier in the talk. And now I hope to say why. This random matrix, right, is the product of a Toeplitz matrix with a dependent, like a row-wise multiplication. And so Toeplitz matrices are relatively well understood from a random matrix perspective, although a lot of that work happened in the past couple of decades. You know, if I just had this random matrix on the right here, that type of random matrix is also relatively well understood. But the multiplication between them, especially because they are dependent, because this matrix is actually a submatrix of this one, is not so well understood. And so this is actually like a challenge that, you know, if anybody who sees this talk has ideas, we'd love to hear from you, because we're working on decoupling arguments, but, you know, we're not really sure what we're doing here. All right. So I guess that kind of brings me to the end of this talk, the conclusion and discussion. So just bringing it back, I talked a lot about preference dynamics as motivation, these idea of assimilation dynamics and harmful recommendations, and how using these models is actually important if we want to design reliable algorithms. And then I turned to the question of actually learning the models, right? How do we just take pure data alone and learn models of these phenomena? There's a lot of open questions here. I spent some time talking about the sample complexity question. I think there's also questions about developing algorithms that work for marginally stable systems. Then there's the question of what do we do once we've learned models? Like, can we accurately predict or filter using these models to predict people's preferences as they change? How do we design optimal and adaptive control algorithms? And control here would really be recommendation algorithms that account for these dynamics. And then how do we actually port these into applications of real recommender systems with all the messiness of them? So I think with that, I have just a couple minutes left for questions. These are the three papers that I talked about today, two of which are on arXiv, one of which hopefully will come soon. This work was not just done by me, but also all of my wonderful collaborators pictured here. And then I'm happy to take a couple questions.
Thank you very much, Sarah, for the great talk. Let's open the stage for questions. You can either type in the chat and I can read for you, or you just raise your hand. Maybe I want to start with one, which is mostly, it relates back to the applications you are targeting. So when you look at these assumptions that you made, by the way, very interesting that you are able to get these technical results. But when you look at these assumptions, which one is the hardest one to meet in practice for the kind of cases you look at?
Mm-hmm.
Or can you give me a bit of an intuition of what is the critical aspect here?
Yeah. So I think in terms of like these assumptions here, I would say actually, so I think everything in 3 is like the biggest question for different reasons, and I think different at different levels. I think probably the most difficult one is this strictly stable assumption. The good news is I actually think that there's some ways to relax this assumption. But I think this is maybe the most objectionable one. So strictly stable means, right, that it essentially means that somebody's preference like decays enough over time. And so after a sufficiently long window, the effect of some recommendation a long time ago no longer matters. And I'm not sure this is true. Like, I think that actually there can be very impactful things that persist for people. And I don't think like maybe unstable preferences is not so realistic, right? Like, your preference is going off to infinity, not necessarily, but marginally stable. So there's like some persistence of memory, I think is reasonable. So I think that's probably the worst one. The good news is, right, I have some ideas for that. The other questions are about like observability, controllability. So like these are natural assumptions And they actually really come from the Ho-Kalman decomposition side, where we want a state space representation. And so maybe we don't actually need state space representations for some of the applications, and that's how we'll deal with it. But I think observable and controllable, it's sort of like your preferences may not be fully controllable, maybe partially controllable. And so I think relaxing it, or even testing, like how much are you affected by recommendations? Like, are people's preferences just changing over time because like things are evolving in the world more broadly and internally? Or is it recommendations are actually actively shifting somebody's preference? In this model, we're actually assuming that they are by definition. And I think that's maybe something that shouldn't be an assumption.
I see. Thank you. Yeah. I mean, I had a doubt. I had an intuition for this, but it's nice that you confirmed this. And I guess also the follow-up question would be for the more complex case, which would be the non-bilinear one. I wonder. I mean, okay, it's not a technical question. I should have to think more about it, but sometimes you can leverage knowledge about the way you can linearize a nonlinear system to derive some properties. Would that be the case here as well? Or maybe you are not even interested in this kind of systems because they don't characterize these applications you
Yeah. No, I think those are potentially important. I think like at this stage, I'm focused on like the simplest models that are reasonable as a way to sort of build up the technical toolbox. I have some guesses that like these simpler models correspond to different approximations of nonlinear systems. And I hope that they do actually, because, right, of course, like I guess in these assumptions, I didn't even list the linear assumption, like that was already, just part of the setting. And I think that's also, again, somewhat questionable. And so making the connections to different types of approximations is something that I hope down the line to do.
Okay, thank you very much. Any question? Another question for Sarah? Oh yeah, did you go ahead?
Thanks for the talk. I have a question about the role of the interaction among users. Well, besides the personalized recommendation, different users may also interact with each other, thus causing some preference shift. So what do you think is the, let's say, the sensible way of modeling such interaction? For example, consensus matrix or mean field effects, and what will be the implication for utility optimization or reducing harms?
Yeah, that's a great question. So I think there's a couple different answers or ways to model this. One answer, let's see if I can find this first diagram. Maybe one answer, let's see. One answer if I'm focusing on a single user at a time, which might be reasonable if you're focusing on building the preference dynamics, is either their social network is sort of fixed. And so everything that has to do with, and it's fixed and unmeasurable in some way. And so everything that has to do with like those effects of other users is just like in this state update, you try to model it as just part of the natural evolution of the state in the absence of recommending content. That's one option. It's obviously like not the best and there's some downsides to it. Another way is if you are on actually like a social media platform where you see interactions and you can use that in your modeling is, instead of modeling this as like just your policy and a single user is, something more multi-agent in flavor where you actually you observe additional, maybe not recommended content, but like additional inputs or interactions between one user and another. And it could kind of enter into the preference update in a similar way. And in fact, actually, that's exactly the type of modeling that I kind of alluded to, these papers that look at this prior work. One of these papers actually, the Gaetan et al. Paper, looks at bias assimilation, where there's actually not just the recommendations, there's additionally some like neighbor network effects going on. They end up finding that polarization still holds for this, like assuming this particular dynamics model, but it looks a lot like you just add a bunch more inputs. So there's not just the input of the recommender, there's also the input of all your neighbors. And so you can kind of scaffold up these large dimensional models using that. And then there's some like, I think, nice connection to like network theory in terms of like the structure of the overall dynamics that you get. But yeah, that's a great question.
Yes, thanks.
Thank you, Zio. Any other question for Sarah? Actually, I have I mean, this is a far-fetched question, but the talk you gave connected me to some of the things I've seen in a totally different application, which is people changing their preferences when interacting with a travel forecaster, or let's say Google Maps or these kind of things. And they adapt preferences with respect to time versus cost versus mode switches and so on. And in some sense, different mobility providers are trying to estimate these preferences and how to capture new customers and so on. Is this kind of an application you ever thought about, or
Interesting.
am I just seeing a pattern matching here?
No, I mean,
in the
it's
wrong way?
certainly in some sense, right? You're like, this is a recommended route. The user sees the route, and then that could change long term. They're like, well, I don't trust Google anymore. Like, oh, you learn things about like, oh, it's the fastest route, but you don't actually like fastest route. You like to avoid highways or something.
Exactly.
But yeah, that I can totally see that fitting. It's not something I thought about before. But that's actually super interesting. Yeah, actually, if you know of any like papers that talk about these types of things, I'd love to. Love to add an example.
I will reach out.
That's a nice sort of like, it is like a little bit of a human behavior example, but it's also a little bit more like cyber physical systems-y, which is cool.
That's great. That's great. I'll reach out when I have the paper.
Yeah. Cool.
All right. I think that's it in terms of questions. In case you have other questions, feel free to reach out to Sarah. But for now, thank you very much for giving this great talk. It was a pleasure to have you here. And also, thank you everyone for joining, and I'll see you all next week for the next talk. And Sarah, I will reach out with the video once I edited it.
Okay, great. Sounds good. Yeah. Thanks, everyone. This was fun. All right.
Bye-bye. Take care. Have a great day.